So we're going to continue talking about fluids. We're going to continue talking about fluids and the flow of fluids. So last class period, we learned about the Bernoulli Equation, which is the equation that related pressure, speed, and elevation. That equation was specifically pressure 1 plus 1/2 density 1, speed 1 squared, plus density 1 GH1 equals pressure 2 plus 1/2 density 2 V2 squared plus rho 2 GH2. Now, I didn't put rho 1 and rho 2 when we did this yesterday, simply because we're never going to have to worry about rho 1 and rho 2. We're going to have the same fluid pretty much. But there are situations, plenty of situations, where the densities can be different. And so this is the most complete form of the Bernoulli equation. And there are different applications, and some different applications actually use different names. So the Torricelli equation is actually just Bernoulli equation, but for having, I think Torricelli's is the same elevation. And so if they're the same elevation, then those two terms are going to just subtract out, and they don't matter, and you change the name. So I only talk about the Bernoulli equation because any of these other situations with the special name are just the Bernoulli equation in a special situation. I couldn't hear that. What was the question? Southwestern, did you have a question there? Guy in the teal colored shirt with the hat backward, weren't you? No? Okay. Okay, so a very simple example of Torricelli's theorem, which is just the Bernoulli equation in a special case. Actually, I was wrong. It's a change in elevation, but not a change in pressure, is what happens when you have something like water coming out of a reservoir here. You have a dam, the water at the top of the dam. What's the pressure going to be at the top of the dam? 1 atmosphere. Okay, now I'm going to go to gauge pressures just to make it easy. So we'll say 0 at the top because it's gauge pressure. The pressure with respect to atmosphere is 0. As I go down the water, what happens to the pressure? It goes up. So I get down here at, depth H, and my pressure is going to be increased by density of the fluid, rho, times G times that depth H. Now, I have a hole and the water comes out. What's the pressure outside? It's still an atmosphere outside. So the pressure inside here was, rho GH above atmosphere. Outside is just atmosphere. And so I have a pressure difference. And of course, I can just say, okay, let's take a little brick of water. I put a higher pressure on one side, a lower pressure on the other. There's going to be a net force to accelerate it. And so it's going to speed up. So we can actually use the Bernoulli equation to calculate the speed. Before we do that, I'm going to do my little demonstration here. So I have this container that has, these things aren't pointing the same direction, maybe it's better. It has 2 holes, one that's high and one that's low. I'm going to plug the top one, pour some more water in, and then let it flow out. And of course, because of the different elevations, the pressure will be different on the inside than on the outside. What do you expect to happen if I have a lower elevation, a bigger depth of water? What's going to happen to the speed it comes out? Okay, so, everybody has an idea here, but we, of course, want to test it. So, that one didn't go very far, and that one went really far. And this is part of the reason why this classroom is not ideal for physics. Well, now the top one is, the water's below it. But you saw that the one below was shooting out faster, went a farther distance, even though it started lower. And the noise is actually annoying. Another thing to notice is, notice here the water looks like it's a nice narrow stream. But as you go down, it breaks apart. We're going to talk about that more in today's lecture. So there's 2 things here noticing, the water speeds are different from one elevation to another because of the different pressures. And then number 2, the difference in the way the water is flowing when it comes out compared to later on. So our first clicker question here. What is the pressure on the water when it exits the hole in the dam, or the hole in the little example here? Yes, clicker question. That's correct.
We can hear them a lot better down there in this room. And we can see them a lot better.
What's the pressure of the water when it, like as it exits?
The pressure outside of the hole. So the water when it comes out. All right, moving on. The answers we had here were 14. Wow. I didn't think it was that shocking personally. 25. 4. Okay, so we have a variation of answers here, and let's see who feels like answering. Who feels like, yeah, that's right. Everybody feels like being the one I grabbed. Actually, don't think that person's class. Wagner Segura. Not here? Okay. Then we'll try Caitlin Toy.
I picked C, and I don't really have a reason. It just made the most sense to me, just because I knew it wasn't A, because it was no longer inside the dam, and I knew it wasn't 0, so.
Okay, so Caitlin said she eliminated A because it's not inside. Changing the environment probably changed the pressure. Wasn't B because she was pretty certain it wasn't a vacuum. A vacuum being no pressure. The water wouldn't be pushing on anything because there's air out there. It's got to be pushing on something if there's air out there. Didn't get to D, but there is a way of knowing. We put those on here because every now and then there is a question where, yeah, we just don't know the answer. But the correct answer is 1 atmosphere because you just have air pressure pushing on the outside. And so that's how, as I said before, we could take a little piece of water and say on this side it's rho GH is the force pushing in and pressure atmosphere plus. And on this side it's just pressure atmosphere. And so we have a difference in force, and Newton's second law says that's going to give us an acceleration. And we can go through and calculate things. It's not convenient. We're not going to do the calculation that way. We're just going to go with the way we did it with the Bernoulli equation. So with the Bernoulli equation, I can calculate the speed the water comes out by saying the pressure inside plus 1/2 the density of the water times the speed, not H. Speed inside squared plus density of water G times the height inside must be equal to the pressure outside So there I've simply taken my Bernoulli equation and I have to decide where am I going to compare with. So looking back at the dam, I could choose there to compare, or I could choose down here to compare. Either one will work correctly. So which do I choose? Well, why will they work correctly either way? Because it'll just change this term to be equal in either case. So let's use the top of the container because that's the most convenient. So I'm just going to say for inside, I'm going to change that to the top as my inside position. And then solve for the speed outside. So if I look at the dam, how fast is the water dropping as the water is coming out of the dam. So what? But how fast? Like how many meters per second do you suppose? That's the acceleration of gravity, but the actual speed at which the water level is going to drop in the dam is going to be negligibly small, right? I mean, you would have to be a huge chasm to actually be able to measure how fast the water is dropping. So we'll say that the speed at the top is approximately 0. Stay. So that's approximately 0. And of course, we're going to find our speed as a function of the height at the top. What's the pressure of the air at the top of the dam? 1 atmosphere. So I'm going to put an arrow to put 1 atmosphere there. What about the pressure outside? It's also 1 atmosphere. And then I have to set a reference for my height, so I'm going to set my reference for the height outside as 0. So the level of the exit is the 0 height, and then the top is h. So now I can just solve this for the speed outside. Notice if I subtract atmospheric pressure from both sides, then these first terms subtract out because they're equal. And I'm going to have simpler equation by far. And so to solve this for the speed out, I just have to multiply both sides by 2 over the density of water. So I can cancel. Density of water cancels on both sides. And I'm going to have the speed out squared is equal to 2g height of the top, or square root both sides. And I get the speed it comes out is, and of course you would have a plus or minus, but I don't care about direction, so clearly I don't write it down. And so that's the speed it comes out with. Now, that should look reasonably familiar because you've done enough problems that you know that if I took a ball and dropped it from height h, no matter what path it takes, as long as there's no friction or non-conservative forces, that ball would have had a speed, a square root 2g height as well. So the water actually comes out the same speed as if I dropped it from the top of the dam down to the level it comes out. Any questions about the dam? Yeah, Paris.
So what you just found is the speed the water is dropping?
This is the speed at which it exits. And it doesn't matter if I have a nozzle pointing up, down, or anything else. That's the speed at which it exits. So here's a simple question. You can have this asked, how high, if I put the spigot so it's pointing straight up, how high will the water stream go? Well, once it comes out, you would just use energy calculations. It initially has a kinetic energy of 1/2 mass, which would be density volume, times the speed squared. And when it gets to its highest point, its kinetic energy is going to be 0, but its potential energy will have increased by mass, once again, density times volume, times g times h. And so if you do that comparison, you find that it goes back up exactly to the same height, just like it would if a ball. If I have a ball and I have a tube, I drop it from here, it'll go down and come back up to exactly the same height if there are no non-conservative forces. So that calculation was assuming there's no air resistance. And the truth is, once you have a stream of water, not just the first bit, but a whole stream, there is virtually no air resistance, so it should come up that high. Yeah, questions? Yeah, Mahala.
So then that answer what you said earlier about how it spreads out of the bottom of the stream, is the air resistance, is that?
We'll talk about that a little more. It is partially air resistance, but it's also partially that you have different speeds of the fluid. As I talk about this reminds me, I grading tests again yesterday. Make sure that when you answer the test, you actually show some physics. There were a few people who simply said well, I take the equation for no friction and they just put the final equation, did no physics in the answer whatsoever, right? In this class, as when you're doing your work and your concept, it needs to be about doing the physics. It's not just, well, I memorized this equation that is derived from physics and put the numbers in. So make sure that when you do the problems, you don't just say, oh, here's an equation, I put the numbers in. I want the physics about how you get there. Okay, a real life problem. Except for there is a really poor assumption that we'll see how to deal with in the next couple slides. You have, when I was teaching at PUC, I was part of the England Volunteer Fire Department. So we had things like this, we're spraying water on things. Actually only got to go fight 3 fires, but we did lots of practice. And for lobbing just a nice stream of water, not to spray anything, you need about 50 pounds per square inch of gauge pressure at the nozzle, which is 3.5 times 10 to the 5th pascals. Well, if you are at the top of the stick there, you're at a higher elevation. What happens to the pressure as you go up? It goes down. I heard somebody in Southwestern answer that one. Somebody here too, but yeah, the pressure goes down because the elevation went up. And so that means that the fire truck is going to have a higher pressure at the engine than where the firefighter is. And so when you're working the fire, you always have an engineer here at the engine, working at the engine, and they're adjusting the pressure so that you have the right pressure at the nozzle. And so we'll do a quick calculation that is less sophisticated than what the firefighters do for what pressure you need to have at the engine. So we say we have an elevation of 10 meters, and we have to have a gauge pressure of 3.5 times 10 to the 5th at the nozzle. And so what gauge pressure do I need to have at the engine? Now, notice with Bernoulli's equation, it just says pressure. Pressure plus this plus this. If you use gauge pressure on both sides, the gauge subtracts out, and it's going to be correct. If you use absolute pressure on both sides, it will still be correct. So you can use gauge pressure or absolute pressure with the Bernoulli equation. Just make sure you use the same thing on both sides. And if in doubt, absolute pressure should never steer you wrong. So I'm going to have the pressure engine down here, height engine equals 0, speed engine, I don't know, that's the speed of the water at the engine. And I'm going to have up here the pressure at the nozzle, the height of the nozzle, which is 10 meters, and the velocity at the nozzle. Now you might immediately say, wait a minute, I have 2 unknowns here. I have the pressure nozzle is a known, by the way, 3.5 times 10 to the 5th pascals. I have the pressure at the engine, actually that's, 3. Pressure at the engine, the velocity at the engine, and the velocity at the nozzle. So how can I do this? If it's just one hose the whole way and the area stays the same, then my naive approximation of no friction says that the continuity equation says the speeds are the same both places, and I don't have to know it because that will also subtract out. If I know that I'm changing from like a 5-inch where it leaves the engine to an attack line that's only 2 inches in diameter, well, then I can once again use the continuity equation to calculate how the speeds relate, and I'm still good to go. So for my problem, I'm going to say it's just one, let's say, 2-inch, I don't care, hose that goes from the engine to there. So all I need to do is say the speeds are the same. So I'm going to have speed engine equals speed at the nozzle. And now I'm going to put everything into my Bernoulli equation. So pressure at the engine plus 1/2 density of water, speed at the engine squared plus density of water, G, height at the engine equals pressure at the nozzle. Now just subtracting. If velocity at the engine and velocity at the nozzle are the same, then those are going to subtract out to 0. And the height of the engine was already a 0. And so I get the pressure at the engine minus the pressure in the nozzle, I'll put it that way, is equal to density of water, G, times the height of the nozzle, which would be density of water, if it's 3.98 degrees Celsius. And so you just multiply those together. This is actually a pretty simple calculation. So we have it's 9.8 times 10 to the 4th pascals is the difference in pressure. So if the pressure at the nozzle is 3.5 times 10 to the 5th pascals, then the pressure engine minus pressure nozzle is equal to add those together, and that's just going to be 4.5 times 10 to the 5th pascals. Notice using significant digits, it wasn't 4.48 because we only had the two significant digits. When we did the addition, it was only good to 10 to the 4th. Now that was naive. Why was it naive? Because we were pretending that there's no drop in pressure as you go through the hose because of friction. But there really is friction between the walls of the hose and the water. And the water does not flow perfectly freely. There's friction between the water. So our next topic is to deal with the ideas of friction in the fluid. So this picture is showing smoke rising. When I was in college, I had friends who went to University of California, Santa Cruz, UCSC, to take their physics class because they were looking for something easier than what's taught at a normal college. And their lab TA, this was UCSC, brought in some of that illegal herb to create the smoke for their demonstrations here. They thought that was pretty funny. Kind of kicked back there at UCSC. So, as the smoke rises, it goes faster. As it goes faster, it changes from a nice smooth flow. We call this smooth flow laminar. And laminar is a simple word. It means layered. Laminar flow means it's flowing in layers. So the smooth flow is laminar flow to something you can see going from here to here. There's some kind of transition region. You still have what looks laminar on the left side, but it's starting to look more chaotic on the right side. And then up here you have turbulent flow where it really is fairly chaotic. Chaotic doesn't mean you can't calculate it. It simply means that it's really complicated to do the calculations, and usually we do something like, with chaotic things, you can calculate this far ahead, but you can't calculate so far ahead. So it's a chaotic flow there. So let's learn how that happens. First, the difference in turbulent flow and laminar flow. In the laminar flow, you notice here, it shows different layers with different speeds. So each layer has its own speed, and you have just one layer on top of another. Now, of course, in real life, these layers aren't segregated as it seems to show here, right? It seems to show all of the region below that red line is one speed. All of the region between the red line and the blue line is a different speed. That's not really what happens. What really happens is you have a continuous increase in speed as you move up. But, we all knew this. When you're at a reasonably slowly flowing creek, the speed of the water right at the edge of the creek is really slow. But you get out in the middle, it's going much faster. That's because of a friction in the water and a friction between the water and the edge. And so you have these layers or lamina that have different speeds. The picture on the right shows a turbulent flow where you have something that breaks it up, and so the water starts making little loops or eddies. And you can actually create cavitation, which is because of the motion of the water, you create little pockets where the pressure is 0. We call that a vacuum. And then you form little bubbles. And of course, those bubbles will be filled with water vapor, but they start as, a vacuum. And so that's what's going on with turbulent flow. In your house, you probably notice this. When you turn the sink on just a little bit, it doesn't make much sound. Turn it all the way on, you start to hear water rushing through the pipes. You're hearing that water rushing through the pipes because you're creating turbulence in the pipes. You don't hear it if it's a laminar flow because it's nice and smooth. But that turbulent flow, you then hear this water in the pipes. So this is caused because of the friction force between the liquid and itself, as well as between the liquid and whatever's containing it. So a vocab word, and yes, it's a clicker question. What does laminar flow mean? Okay. Hopefully everybody's got their answers in now. So we only had answers for the top 3, and it looks like it's pretty clear there. I won't call on somebody. Laminar flow meant flow in layers. It's not actually uniform because the speed is different depending on where you are. But it's uniform in terms of this layer is all the same. This other layer is all the same. Viscosity is the measurement that we make of how well the fluid flows. And so the viscosity is actually measured by making 2 plates, putting a fluid between them, and having them slide. If they slide really easily, that means there's a really low friction between the plates and the fluid and the fluid, actually. And so it's a low viscosity if they flow easily. It's a high viscosity if they don't flow well. Looks like our camera's, okay. Camera's breaking up there. And so what they actually do is they make 2 plates, or if you want to be really honest, they do it with the drum. You have a cylinder, and then you have another cylinder outside, and they spin one cylinder and measure the force on the other cylinder. And so they measure the force that's trying to make the inside cylinder rotate when the outer one is rotating, the separation between the 2 cylinders, and the speed at which the rotating one is rotating, and they calculate this viscosity. Who knows what that symbol is? Eta. That's eta. It's the Greek letter eta. And so it's written ETA in English. Capital Eta looks like this. So if you're putting it on the keyboard, you go like into your symbol font, and it's the H key to get eta. And so viscosity has the symbol eta. And it's the force you have on one surface due to the other surface multiplied by the separation between the surfaces divided by the speed of one surface with respect to the other and the area of the surface. So practical things about viscosity. We measure viscosity actually a lot. But first let's start with simple comparisons. You have syrup that you can pour in your pancakes and orange juice that you can pour in your cup. Don't get them mixed up. Of those 2, which one flows easier? The orange juice. Because it flows easier, that tells you something about the viscosity. The lower the viscosity, the smaller the force is going to be between the fluid and the easier it flows. So that means your orange juice has a lower viscosity than your syrup does. Question?
We're trying to figure out what L is on
that. L is the separation between the 2 plates. Right? You have a plate here, and so L is that perpendicular separation. So things that flow easily have a very low viscosity. Things that don't flow well have much higher viscosities. So if I were to ask you about molasses, would that be a low or high viscosity fluid? High. What about motor oil? Okay. I heard people say low. Your motor oil serves a very simple purpose, and it's because of its viscosity. In your car's engine, you have steel pieces. And you don't want the steel to rub on steel because you will then wear away the steel. And so the goal is to have a layer of fluid between the steel so that you don't have steel on steel. So it needs to have a high enough viscosity that the steel on steel, or the steel doesn't squeeze it out. But it needs to have a low enough viscosity that it doesn't significantly interfere with the engine rotating. So the viscosity level of that oil is important. If it's too low, then you have engine wear. If it's too high, you have a harder time getting the engine to turn. So when you put motor oil in your car, I'm sure somebody here has put motor oil in their car recently. What did you use for the oil that you put in? Not Penn's oil, but what grade of oil?
10W.
Okay, I had somebody say 10W30. 10W30, the W actually stands for winter. So that's 10 winter 30, and they never show it, but it's actually S for summer. So when you put in 10W30, it's 10W30S, if you want to be technical. What those mean is winter is cold temperatures. And a 10-weight oil will have a viscosity of around 7, and we haven't looked at the units. It'll have a viscosity of about 7 Pascal times seconds at, I think it was minus 30 degrees Celsius. The 30 weight, it actually has 30 weight written in our textbook for viscosity, and I think it was somewhere around 10 for the viscosity at 130 degrees Celsius or something like that. So you have different viscosities for different temperatures, because when you start the engine, when it's cold, like here in Lincoln, it does get to be minus 30 degrees Celsius occasionally. You want the fluid to still be able to squeeze in between the metal, and most fluids start gelling as you get colder. And so the viscosity would go higher and higher as it gets colder, and so you would have a hard time getting anything in between there. It's hard to turn the engine over. So you want a relatively low viscosity when it's cold so that you can turn the engine over. But then you want the viscosity to not get super thin when you get up to running temperature, because it would naturally get lower viscosity as you got hotter. And so these multi-grade oils are made so you have different behaviors at low temperature versus high temperature, so you keep a somewhat flat viscosity for the actual viscosity as your temperature changes. Of course, I don't know how cold it gets there at Southwestern, but if you don't get to freezing temperatures, you probably don't need a multi-grade oil. You can just put in 30 weight oil and be good. Okay, looking at the flow through a pipe. The picture on the left is a non-viscous fluid. Do non-viscous fluids exist? Kind of. A superfluid is a name for a fluid that has no viscosity. That means there's no forces holding the molecules together in the fluid state, which sounds pretty unusual, because if there's no force holding them together, they should be free to leave and you would have a gas. But you can make a superfluid helium. Helium-4 forms a superfluid because you make Cooper pairs. It's helium-3 that forms Cooper pairs, my bad. Helium-4, because it's a monatomic molecule that has the right properties, you get it cold enough and it can actually have virtually no viscosity. What does that do? Well, I mentioned last class period using filter paper and your Buchner funnel and stuff. Well, you can have a filter paper that has a porosity so low that helium won't go through easily. So you pour it in there and the helium just basically, liquid helium stays on top. How do you get liquid helium? Really, really cold. I forget what the phase transition temperature is, but it's something like less than 10 kelvins. Yeah, I don't remember the number. So you have this liquid helium there, it just sits there. But if you actually get it cold enough for it to go through the transition to a superfluid, it suddenly just flows through like there is no filter paper. It just goes right through. And the reason is it couldn't go through because of the forces holding the helium molecules together. You get to low enough temperature so the viscosity goes to 0, and suddenly each molecule just goes through one after the other without any problems because they're not being held by others. It's really cool. It also makes capillarity really interesting. Let's climb out. So in a normal situation, you don't have this superfluid. Everything has viscosity. So you're going to have material that's next to the walls goes slowest, material that's the farthest from the walls goes fastest. So in a normal pipe, you should have the fastest flow rate in the center of the pipe, the slowest flow rate at the edges. Excuse me. How does this play into anything? When we used our demonstration with this, I pointed out the water breaking up. If you're going to make a water fountain and you have water come out of the nozzle, it's naturally going to be speeds like you see here in B. So the water on the outside is going slower, the water on the inside is going faster. And so as the water travels away, you're going to have it start breaking apart because of the different speeds. And so the water naturally breaks apart and you get a broken stream. So how can we make fountains so they work better so they don't break up as much? Or a fire hose. How can we make a fire hose so it throws a nice stream of water instead of breaking up? Anyone have the answer? IRR people? You guys study fire nozzles? No? Well, how do you make the water so it behaves more like this so it doesn't break apart in a fire hose? Low friction hose would be an idea. What we actually had, at least in the nozzles I had to take apart, was something that looked, at the top, it kind of looked like a potato smasher. It had a grid like this. And of course, it was in a circle. And it was, centimeter or two thick for the pieces. So the water was broken up into these little square sections. And each square section would have a speed profile like shown for that tube. But the center of each one would be the same speed. And so when it goes through that and then comes back together, you have a much closer to same speed everywhere. Because what you'd have, if you look at the speed profile coming out, is your speed profile. So I'm just going to have low speed is here, high speed is here. It goes like this. And so it's more similar speeds throughout, and the viscosity will actually pull it so that you get very far away, and your speed profile would be more like this, and then it's able to stay together. Now, if you're making, for the mall, they want to have a nice fountain that shoots a water stream 30 feet. They essentially do the same thing. They get a whole bunch of those little straws, like, the little straws people use in their coffee that you can't suck anything out of. Just pack those together in a tight bundle and you force the water through. You're going to have a very close to uniform speed when they come out. And so that will make a very nice, stream of water. There is one other trick, putting in things to make it so it has a higher surface tension so it holds together better. So that's a practical application for fun things. Well, fighting fire is not a fun thing per se, but now the bad approximation of pressure not dropping when you go through a hose. Because of viscosity, there's going to be friction, there's going to be a force opposing the flow, and thus you're going to have a drop in pressure as the fluid goes through any kind of hose, whether that hose is an artery in your body or a fire hose or a garden hose. So, anybody here actually know how to pronounce this gentleman's name? I looked it up before class. Yeah. I found a whole bunch of different pronunciations, I think most correct is something like PHYS. I always learned, because I learned in America, to say PHYS. Clearly not the right way, but it's the way an American reads this. So I learned it as PHYS law. This is a law that tells you how much your friction loss is going to be. So when the firefighters, the engineer that's controlling the pressure at the fire engine, when he's sending the water out there, he has to sit there and say, okay, how long is the hose? If I have this long a hose, I'm going to need to push up the pressure this amount to compensate for the frictional loss. So the longer the hose, the higher the pressure needs to be at the engine. And the calculation turns out to be not all that difficult. Q, we saw, yes, last class period. Q is the flow rate. So Q is equal to the cross-sectional area of the hose multiplied by the speed of the water in the hose. Now, if you have continuous flow, that Q is going to be constant throughout. R is a number that they just call the resistance. It's the flow resistance. And that flow resistance has what is that character again? Eta. And what it stands for? Viscosity. Times the length of your tube divided by pi times the radius to the fourth power. And so if you put R in, you get this equation that's in the middle. So that's PHYS law. That's an equation to help us calculate how much pressure is going to change when you go through a tube. Now, I just remembered I started saying I haven't talked about units yet, and I never finished it. The units for viscosity. It's force times distance. So let's just put force is measured in newtons. Distance is measured in meters. Divided by speed, meters per second, times area, meters squared. So you put that all together, and that's going to be Newton meters per meter cubed, and seconds on top cancel 1 meter, and I have newtons per meter squared times seconds. But a newton per meter squared we have a simpler name for, a Pascal. So that's a Pascal times a second. And there's a name for a Pascal times a second, although nobody uses it. A Pascal times a second is called a PHYS, which has an abbreviation of PL. So that's your SI unit for viscosity, the PHYS, or Poisson, any of the other pronunciations you want. There is another unit that you actually see more often than the Poisson, and that's the PHYS. That's just dropping off the second half of his name. And 1 PHYS is equal to 0.1 Poissons, or in other words, 0.1 pascals times seconds. So the units there, as far as I'm concerned, we don't need to worry about learning the Poisson or the PHYS. Just if it comes up somewhere like, say you're taking the MCAT, so you have that knowledge that it exists. For our work, we'll simply say pascals times seconds, which should be clear to everyone. So that's the units there for viscosity. Let's look at a practical situation. This would be my father. About 19 years ago, he suddenly went from perfect heart to 90% occlusion. And if he has 90% occlusion, that's 90% blockage. That means the radius of a coronary artery was equal to 1/10 of what it was initially. What's going to happen to the flow rate if you have the same pressure difference from one side of the artery to the other? Actually, I take that back. It's r squared. It's the area. Area is pi r squared. My mistake. You might want to go back and change your answers for that mistake. Okay, I'm going to close it up in about 5 seconds. Okay, we got 8, 8, 28, and 9. Now, I fear that if I were to have you discuss it with people, we would move further to the wrong answer, so I will go through the right answer right here. So we have the radius of the artery squared is 1/10 the radius that it started at squared, right? Because the area is 10%. And so if I look at my flow rate equation, that's going to stay the same. The viscosity of the blood is going to stay the same. The length of the artery stays the same. So all of that is a constant. And then I have times pi radius to the 4th power. Or if you prefer, all of this constant stuff, I'll put pi inside the constant, times radius squared squared. So since radius squared was 1/10, radius squared squared is going to be 1/10 squared of what it started. So I'm just putting the brackets to indicate the stuff that's constant. And now I can cancel everything except for the 1/10 squared. So the flow rate would be 1/100th as much. My father was getting 1/100th as much blood through that artery as he was a year ago, before that. And so, of course, that's going to be, the correct answer is the 1% of initial flow rate. And so that's where you got to do something to get blood through that artery, or you have muscle dies. Okay, the last thing for today is going to be on the transition from laminar to turbulent flow. This picture on top simply shows a pipe that is decreasing in radius. As it decreases in radius, we know that the speed of the fluid has to increase. And so as the speed increases, the speed at the edge is still going to be approximately 0 right at the edge. And the speed at the center has to be much faster, so you have a much bigger change in speed as you go across the cross-section. That bigger change in speed means that you might have more force trying to push the water along than you can have between the molecules trying to hold it back. And that's what causes us to have the turbulent flow. And so you have turbulence occurring back here because of the higher speed. So turbulence has to occur because of the higher speed, and we saw that in our first picture with the smoke. So how do we determine if a flow is going to be turbulent or not? We calculate this number called the Reynolds number. There are two equations here, one for just a flow of a fluid in a circular pipe, one for an object, like let's say a rock going through a fluid. So you have different ways of calculating depending on which one it is. Rho is the density of the fluid in both cases. V is the speed of the fluid flow if it's the fluid in the pipe, speed of the object compared to the fluid in the other. And you have different rules of thumb. If you have an object in the fluid, so that would be going to this one here, then if the Reynolds number is under 10, it's definitely going to be laminar. And if the Reynolds number is over 1,000,000, it's definitely going to be turbulent. That's a pretty big range in between. What happens in between is you have a transition where you might have turbulence some places and laminar some places, like we saw on that picture with the smoke. Now, if you have a circular pipe, the difference between them is smaller. Our textbook says 2,000 and 4,000 for the Reynolds numbers for laminar flow versus turbulent. This is the last slide I had. The Magnus force explains why curved balls curve. Did you have a question? Just angry that I went to the last slide.
Slides.
You don't need to write down all the equations. They're in the textbook. But I thought it would be interesting to people to see why you can, curve it bend it like Beckham. That's what that movie was. You put a spin on the ball. Now, these pictures are opposite to each other. Notice the spin direction here is that direction. Spin direction here is that direction. So they're curving the opposite direction. I tried to find things matching. But what happens is you actually separate the air so you have more air going on the side that's being pulled by friction with the object. But having more air there creates lower pressure, and thus it bends toward that direction. So that's all we're going to have on the Magnus force.